This lesson is going to discuss how to multiply and divide rational expressions. Now remember, a rational expression is a quotient, that is a fraction, that has a mathematical expression up top in the numerator as well as one in the bottom in the denominator. So here we are given a problem to evaluate, and we have a rational expression multiplied by another rational expression divided by a third rational expression. So how do we solve this? Well, the first thing that we're going to do is we're going to change this division. So I'm going to go ahead and just write the first two terms as they were. And I'll just use a dot to indicate the multiplication so we don't get all the x's confused. And x is on the bottom there. And then this division here is going to turn into multiplication. And by flipping, if you like, the top and the bottom. So we'll take the 5x squared that used to be in the bottom, and we'll put it up top. And the 5y, well, that can go down to the bottom. Okay, now what's the rule for multiplication? Well, it's quite simple. We just multiply top times top times top, and bottom times bottom times bottom. We'll look at the coefficients in front first, and we see that we have an 18 and a 5. Well, if I multiply those together, well, 10 times 5 is 50, and then 8 times 5 is 40. So this is going to give me a 90 up top. X cubed times x squared is x to the 5th power, and then y cubed is the only y term we have. Down on the bottom, well, we just have 3 and 5, which is 15. We have x times x, which is x squared. And then we have y times y, which is y squared. Okay, well, we can reduce this now. We know that 15 goes into 90 evenly. And in fact, it is going to divide in 6 times. If we have an x squared in the bottom and an x to the 5th power up top, we know that the x squared will cancel out 2 of these x's, resulting in an exponent of 3. We subtract the exponents. And then we've got y squared and y cubed. Well, the y squared will result in 1y up top. So our final answer in this case would be 6, and we've got x cubed, and then y to the exponent 1. So there is the evaluation of this original mathematical expression. Now, you'll notice just one quick little thing here, that we went ahead and we multiplied all the tops together and all the bottoms together, and we got some pretty large numbers. So we had 90 up top, 15 down the bottom, and then we had to simplify. A better strategy might have been to perhaps simplify before we multiply. And that would allow us to work with smaller numbers. So for example, if I look at the 18 over 3, well, that's the same as 6 over 1. And if I notice that I've got an x in the bottom of the first fraction and an x cubed up top, that would result in just x squared, and then I just have a y in the bottom. Similarly, well, y cubed over x, that is just y cubed over x. And in the final term, well, 5 over 5 is 1 over 1, so the 5's cancel out. And then I've got an x squared on top and a y on the bottom. Well, that looks a whole lot simpler, because now when I multiply it together, I'm getting 6 and then x squared y cubed. And down on the bottom, I've got x and y squared. Well, we can also cancel a cross multiplication. So for example, I've got a y times another y. That's a y squared in the bottom. That cancel 2 of those, leaving me with just a y to the exponent 1. I've got an x down in the bottom. That will cancel one of these x's. And if I look at the final answer now, I've got 6 x squared times x to the 1. Well, there are 3 x's being multiplied together, x cubed, and I'm just left with 1 y there. So we get the exact same answer, but you'll notice that if you can look for opportunities to cancel before you go ahead and do your multiplication, you'll be working with smaller numbers and it might be a little easier. If you're more comfortable with going ahead and just multiplying the tops out and the bottoms out and then looking for opportunities for simplifying, that works as well. You will end up with the exact same answer regardless of the process that you use. Let's say we were asked to evaluate this rational expression. Well, again, we have some multiplication and some division. So first thing I'm going to do is I'm going to rewrite this. And while I'm rewriting this, and I'm going to flip this division into multiplication, I'm also going to write it in factored form. And why am I moving to factored form? Well, if we recall, when we write factored form, we create an opportunity to cancel because all of the terms in factored form are joined by multiplication. So if I look at the x squared minus 1, that's a difference of squares, and I have x plus 1 and x minus 1 up top in the first fraction. Down in the bottom, if I take a greatest common factor of 4 out, that leaves me with x minus 1 inside those brackets. Okay, times 8x plus 8. Well, I think I can take out a common factor of 8 and be left with x plus 1. Down in the bottom, x plus 7 is all by itself. And then I'm going to change this division here to multiplication. To do that, again, I'm just going to flip the bottom and the top in the third fraction. X minus 5 now belongs up top. And in the bottom, this is a perfect square. And I know that that is x plus 1 times x plus 1. Okay, now that we have factored all of the terms and they're all joined by multiplication, we can now look for opportunities to cancel. Remember, we can cancel within the same fraction, like this, and we can also, because they're all joined by multiplication, we can cancel across fractions, like that. So if I continue this process, the x plus 1 will also cancel here. And if I look at the coefficients, I can see that 4 goes into 8 twice. Okay, the x plus 7 does not cancel with anything on the top, so it looks like I'm almost done here. I'll just write what I have left, and up top I have a 2, and I have an x minus 5. And on the bottom, I have, quite simply, an x plus 7. So, if I was tasked to evaluate or simplify the following expression, that complicated looking thing at the top there, that simplifies to 2 bracket x minus 5, all of it over x plus 7.